So what we have done for that particular problem was what? We basically defined the appropriate ingredients that we need to solve this problem, and we literally milk down all the information that we can gather from the statement of the problem. Now you see, so this is the unconditional probability of that you select a gold coin, and these are the conditional probabilities. And you have also this information. We'll just bring them together. Either we can just go ahead and use this formula, or just pretend that we never did this, right? Because I told you that you shouldn't memorize it, right? And you already forgot what that was. You start with this, okay. All right. And even then I say, well, probability is not relevant at the beginning. You just take a look at this event, right? What is the event? Event that you select a gold coin, right? So this is gonna be, right? While you are selecting a gold coin, you must have selected one of these, one of the urns. Either you must have selected either urn I or urn, well, okay, let's see, urn 1 or urn 2 or urn 3, right? So these two events are the same because this is, what, by definition, the entire sample space. Nothing else can happen, right? You must have selected one of them, right? G is, of course, right, selecting a gold coin is going to be just a subset of this. So these are the same, right? So this is nothing but the sample space. Well, these are unions. We can just distribute, right? This thing and write it like what? While you are selecting a gold coin, you must have selected, right? Either urn 1, right? No, that's not right, right? Or G must have happened with event 2 together, or G must have happened with event 3, right? Together. Now we know that these are disjoint because at the same time you cannot select two urns, right? Together, right? So you must have selected one of them exactly. And since this is what? Intersection of G with event I, or event 1, right? This is a subset of this event. This is a subset of this event. Since these are, again, disjoint, these two events are disjoint as well, right? And similarly, right, these three events are in fact disjoint, pairwise disjoint, right? And the event G that for which you would like to calculate the probability then can be written as what? We will again use the axiom of probability, which says that whenever you have an event G which can be written as the union of disjoint events, right, its probability is going to be just the sum of the probabilities of those pairwise disjoint events. Namely, in this case, you have that plus the probability that G happens together with event 2 and plus the probability that G happens together with, right, event 3. So we have that, right? Right? So these are, because these are all pairwise disjoint. Okay. Then you always keep an eye on what you have already learned, right, from the statement of the problem, and try to find a tie between these two ends of blackboard, right? So we know that, well, this is again part of the definition of conditional probability, right? Two conditional probabilities, either I given G or G given I. Right? You have to make a choice. Then you take a look at it. What do you know? You know the probability that G given I, but not the other way around, right? So it is perhaps better to write this in terms of those conditional probabilities, right? If you are not fluent in this business, it is okay to write it one more time. So you say, well, okay, I know that in the numerator I have this, and in the denominator I must have what? The probability of this event sitting on the second part, right? And therefore I can write the numerator in that thing as what? Probability that G given that event 1 has happened times the unconditional probability that event 1 has happened, right? So this thing is here because of that equality, plus, but we'll now play the same game for the second one, right? So this is like what? The probability that, okay, I must have picked a gold coin, given that I must have picked before, earn 2, times the unconditional probability that the earn 2 must have been selected in the first stage of the experiment. And, well, the same can be said for this third term. I have that, right? Now we just put the numbers, plug the numbers into this thing. So we know that this is, do we know what it is? 4 over 12, it is 1/3, right? Times, well, these are all what? Equal to 1/3, so we can just take under common parentheses and just worry only about this, right? Because we know these are all 1/3, that's outside, that stays outside the parentheses. So this is 1/3, this probability equals 1/4, right? And finally, what do I have is 6 over 12 is 1/2, right? Right? I have not made any mistakes by now, right? Okay, so this doesn't look nice. Okay, so what does this give me? So 1/3 times, right? Now 12 is the common stuff, right? So we can just look at it like this. This gives 1013 divided by 12, right? Or 13 over 36, right? That's the probability that, or the unconditional probability that we will have selected a gold coin, right? It is, well, significantly less than 1/2, right? This is not a favorable game for us, right? We'll later learn, actually, what is the fair entrance fee, let us say, that you are expected to pay in order to play such a game. But that can wait. Oh, this says that there are a couple of interesting examples from my lecture notes. Let me see. Let me also take a look at them. Right, so this now comes from another textbook, an interesting example. You can also find this statement later if you would like to read. So it's okay, let me read the question first and I'll again take short notes on blackboard, right? An individual, okay, uses the following gambling system at Las Vegas. Is there an equivalent of Las Vegas in Turkey yet? Huh? Cyprus? I shouldn't say that. Okay. He bets, right? He bets $1 that the roulette wheel will come up red. Okay. If he wins, he quits, right? But if he loses, then he makes the same bet, namely, roulette will come again on red, but now bets, right? A second time. Only this time he bets $2, right? At first he bets $1. If he wins, he picks up $1 and leaves. If he loses, now he is short of $1, hoping to recover, I guess. Right? He bets on the same red, but now puts $2, right? He bets for $2. And then what happens? And then regardless of the outcome, right? Whether he loses or wins, he quits, right? And assuming that he has a probability of 1/2 of winning each bet, which might not be quite true if you just think of the game, but just let's assume that with probability 1/2 he wins or loses each time he bets, right? What is the probability that he goes home a winner, right? And the second part is going to depend on the answer, so we will come back to that one. So we would like to know the probability that the person will eventually win the game, right? As I said, this is, you can check the Sheldon Ross's book. You have the information about the textbook on your information sheet, right? Let me also write this information in case you want to read the exercise yourselves in more detail, right? So we have what? A betting game, right? Right? We first bet $1, right? Right? If, right? We quit if we win, right? And if we lose, right? If we lose, what happens? We bet again, right? Bet again, right? But we bet now $2, right? Now, and then we quit no matter what happens. No matter, right? What the result is. Right? In each stage, right, the probability of winning, right? In either of these stages, they are independent first of all. Probability of winning is 1/2. And therefore you can say that this gave you each stage, each single bet or each single game is fair, right? So with equal probabilities you can either win or lose, right? It's fair in the sense that you don't lose with a higher probability than you win, or you don't win with a higher probability than you lose, right? In that sense it's fair, right? Okay, and what do we want to know? We want to know, I shouldn't write like this. Okay, we want to know the probability of, right, going home as a winner, right? I write it like this because you may actually win the game right from the first stage, or if not, maybe in the second stage you have another chance. Okay? Okay, again, this problem is now stated in English, no mathematics or whatsoever in it, right? So we would like to now formulate it using perhaps events, introduce a probability function, and then use probability axioms to solve the problem. If we also need to use the conditional probability, we will do that as well. As I said, there are many ways to solve the problem. I may just come up with two definitions of two events. You may come up with some other two events. They are perfectly fine. All right? Here's what I suggest. So why don't we just denote by W, all right, the primary event that we are interested in, namely the player, player goes home as a winner, right? Okay. And I will also define by W1. You can see that actually this game again is like a two-stage procedure, right? Whether you move to the second stage of this procedure depends actually outcome of the first stage, right? Even it is not a definite two-stage procedure, but there are the second stage is like a conditional stage, right? So W1, let's define or denote by W1 the player, the event that the player wins, okay, wins the first bet, okay? That explains why I put a subscript 1, right? Okay. Perhaps these are enough, right? If I just denote or define these events, what I want can be written as what? Okay, I want to calculate the probability that event W happens, right? That's what I want to calculate. Well, what do I know in order to be able to calculate this? Now let's just proceed with that, right? As in the previous example, right? First write what you want, and then try to identify what you know about the problem that you think will help to find this number, right? Okay, what do I know? Well, okay, what do I know? I know that in the first stage, I will win the game with probability 1/2, right? It's a fair game. And in the second stage, well, first of all, right, I will eventually, okay, or I can write like this. I guess this makes sense. I will go home as a winner, given that I have won the bet in the first stage, with what probability? Huh? Huh? Something between 0 and 1? 1 over? What? Say it again? 1 over 4. Why did you say so? So that's what your friend suggested. Why do you think this? How did you come up with this number?
The probability of the first game is 1 over 2.
Okay. And then you multiplied it with?
1 over
2.
2.
Why is that?
Because it's also.
Okay. Let's just again read. Why don't you read it for ourselves, for us one more time? So what is this? This is the probability. What I am trying to calculate. The probability that we go home as a winner, given that we have won. Okay. So if we win in the first bet, what do we do according to the procedure? Yeah, you just walk away anyway. So there is no second stage in this case, right? And in any case, you also know that you have already won, so, right? So now you definitely know what the outcome is, don't you? You know. So what do you need, what you don't need here? It is surprising, right? So sometimes you know a lot more than what you think. So if you know that you have already won the first stage, you have won the game, right? So you know that now you are going home, right? Knowing that you have actually just did your best and you collected all the rewards, right? So if you, I am just checking this out, right? Nothing else. Since according to this statement, given that W1 happened, namely given that player won the first bet, right? The probability that this guy is going home as a winner, well, with certainty, with probability 1 he is going home, we know that, right? So we have that, but then you can perhaps say, well, you need to work a little harder to calculate this, right? What is the probability that this person is going to go home as a winner, given that he lost the first bet? Huh? It is going to be 1 over 2, right? Not even 1 over 4, right? Because this now is given, we know that he lost, right? There is nothing uncertain about that, right? Given that information, now, well, he has a second chance, so we know that he's going to bet one more time, even though he's betting now more money, right? But the probability of winning will not change from one bet to another, and if this is true, right, the probability of winning at each stage is 1/2, this is going to be 1/2. Is there anything else that I can write right away from what I read from the description of the problem? Perhaps not. This seems like what we can learn at most, right? Okay, then. Now, by using all of this, we will want to calculate this, right? What is the probability of going home, the unconditional probability that we are going to go home as a winner? Well, you just look at this thing briefly, and then you say, okay, well, let's play the same game, right? Even before you worry about the probability, just look at the event itself. Okay, going home as a winner, right? This can happen in two ways, right? Right? Either we must have won the first bet, or we must have lost the first stage, right? So the union gives the total sample space. There's nothing else left. So this is again omega. Therefore, when you take intersection of W with this set, you get omega W back, right? But I do this anyway because I now would like to use this distributive law to write the same event as now the intersection, or this is the event that you go home as a winner, right? because you have won the first bet, or what else can happen? You went home as a winner, but you have lost the first stage, right? Now these two guys are, right, one is the complement of the other, of course they are disjoint, and this is subset of the event W1, and the second event here is a subset of W1 complement. Since they are disjoint, their subsets are going to be disjoint, just the way that we discussed earlier, right? So these two things, right, are disjoint, right? Now to calculate the probability, unconditional probability that we go home as a winner, is going to be what? It is, now W is the union of two disjoint sets, therefore its probability is the sum of the probabilities of those elementary events, right? No, not this one, but just the complement, like this, right? Now, when you come to this point, then you again take a look at these things. We'll try to make both of these look like this too, right? And again, given W1, I know the conditional probability of W, right? So I can write this thing, then W, given W1, times the probability of W1, right? And for this one, I now have the probability that W given W1 complement, right? Times the probability of W1 complement, right? Right? And then let's just write numbers, right? What is this? You won the first stage. Of course, you are going home as a winner with probability 1, right? Well, you have lost the first stage. Well, you play one more time, we know that. And again, the probability of winning is going to be, since this is a fair game, it's 1/2. We know that, right? And what is this? Probability of winning the first stage. Well, this is just another instance of the same fair game. This can happen with probability 1/2. And you lose the same, you may have lost that game, again, with probability what? 1 minus probability of winning, which is 1/2, right? So we have that. So we will multiply and sum all these numbers. From here you have 1/2, plus from here you have 1/4, right? So this is 3/4, right? This is a lot bigger than 1/2, right? So what did we manage here? You started with a fair game, right? First of all, do we have any questions with the calculations? Huh? It's another, huh? Do we have any questions? No questions? So you agree that this number is there. I did not play any trick. No, right? Now we started with a fair game, right? And we used an honest strategy. Did I use any, have I cheated in any way? No. So if I lose, I'll just play the game. I put more money and so on and so forth, right? But by using this honest game, I was able to manage to come up with a winning probability which is a lot more than 1/2, right? Right? So this says that, okay, there is a fair game. If you follow this strategy, out of 3 out of 4 cases, you will be able to win, or 75% of the time, you will win the game, right? So you can actually sell this to a gambler, huh? And you can make a lot of money, right? A gambler. Huh? Yeah, that's the question. Now, why do you think that people would not use such a thing? You lose a lot of money. How did you make the calculation?
Because you bet again and again, it increases $1.
Okay, you bet 1. If you lose 1. Right? But in the second stage, if you earn, if you win, you get $2.
Yes, the probability of losing is decreasing, but the amount of money you lose is increasing.
Can you come up with the numbers? So we need the numbers so that we can compare them. So your intuition is correct. So you have probabilities and profits are unbalanced in this case, right? Here is what you do. We will come back to this thing, but you can calculate actually expected profit, right? it is not so much important whether you lose or win at all, right? If there are stakes, right, that you may lose or win, then you have to calculate how much, right? What the size of the profit you expect to earn, right? So, a quick and dirty calculation for this one would be like this, right? With 1/2 probability, you will win at the first stage. If you win, you take $1 and you go home, right? But with 1/2 probability, you will lose, right? The first bet, you will lose the first bet. And if you lose, then first of all, you lose $1. The $1 that you bet at the beginning, right? You lose. Lose what? So since you lost the first bet, so you lose this $1 you have bet before, but then you bet $2 more, right? So the game is going to continue from here, right? So with probability 1/2, you will win, and you will get $2 that you bet in the second stage. But right, with probability 1/2 again, you may lose the game again, and this time you also lose $2, right? Right? Were you able to follow what I did? Huh? Any questions about this? Are we comfortable with this? For the first stage, right, I bet $1. With probability 1/2, I will win, I may win, and then I will get this, right? But with 1/2 probability, I may lose. And if I lose, I will first of all lose this $1, but I am not completely hopeless. I know that I'll just proceed to the second stage. In the second stage now with 1/2 probability, I will win what I bet, which is $2, or in the second stage I may again lose, which is going to happen with probability 1/2, and then I will lose this additional $2 that I bet, right? So I have this thing, right? What is this thing? If you just, so there is -1 times 1/2, this thing will cancel this entire stuff, right? And here, inside the parentheses, well, this number is the same as this one. They will cancel before even you multiply with 1/2, right? All you get is 0, right? Right? Okay? So what does this mean? So you neither win nor lose on average, right? And this is a famous, important theorem, actually, that's, as I mentioned before, you will see that these are intimately related with martingales, which are used to model fair games and strategies that the people can use in various fair or unfair games. And there is a theorem there which says that if you start with a fair game, there is no honest strategy that will be able to beat that fair game. There is no way to beat a fair game by using honest strategies. What do I mean by honest strategy? You don't cheat. You don't use insider information. You don't use backdoors and just extract some information. Which sometimes happens. So there are, in financial markets, for example, all the stocks that you buy and sell, all the portfolios that you manage, you can just think them like actually a game that you are playing against the market, because you don't know what the stock market is how stock market is gonna fluctuate over time. All right, but if you are not using anything more than what the public is provided, right? All those strategies are titled like a honest game. Then it says that if the stock prices are actually moving like in a fair game, there is no way to make actually extra profit by just using honest strategies. Are there dishonest strategies? Well, there are. That is what people call the insiders, and people who work for the company sometimes use their power. They know, for example, whether their company is going to actually invest in a new technology, or if they are, for example, there are a lot of pharmaceutical companies who actually apply for a new drug to be publicly available for sale to, let's say, health minister, right? Sometimes health ministry will just say that, okay, this drug is not suitable for the public, And of course, before the public knows, the company's upper management will know what the result is, and they quickly, for example, go out and sell their stocks. That happens, for example, that happened in the past. It is unlawful, of course, but they don't tell, of course, all these details, right? So unless you use insider information of this kind, anything that will actually affect, for example, the company's future revenues, if you don't have any access to such things like you and me, right, the ordinary people living on the street, there is no way to beat the market. It might just actually, why am I telling this thing? This is like actually, if you see somebody outside on the street that says that I have a good strategy that will make sure that will guarantee a positive return without risking anything, okay? That's not correct. There is something like this. Mathematically, we know that you can prove, and we only saw an example here actually. There is no way to beat a fair game by using any honest strategy, right? Right? Either you will have to work with the crooks to make more money, right? And then, of course, I don't suggest that you should do that, right? But otherwise, there is no way to make additional extra riskless money. We'll see. We'll probably see more why that is true and what the other examples that you can produce when we start discussing martingales, right? But in this example, now is it clear what happens? Okay, with probability 3/4, right? 75% of the time we win, but the average winning or the average profit that we gain, right, we obtain by applying this strategy is just 0 on average. Therefore, it is not really attractive to anyone outside. I'll actually give an example of this so-called doubling strategy, which actually produce positive profits, but then we will see that actually you need on average infinite amount of money in order to be able to remain in the market until you win. That's also another what we call mathematical defect, I should say, actually, for that, because nobody on the earth will have an infinite amount of money in his pocket or bank account. Okay, we'll see that later as well. Okay, let me see. Okay, this is one example. Here is another interesting one. Okay, again, this is from our reference textbook, right? And it is exercise 30 on page 18. If you would like to check for more exercises before and after this one, there are a lot of other interesting ones. I don't have time to really discuss all of them. Okay, what does it say? Okay, there are two people, Bill and George. Okay? Bill and George go target shooting together, right? So both shoot at the target at the same time, right? Suppose Bill hits the target with probability 0.7, right? Whereas George, independently of what the result for Bill is, right, hits the target with probability 0.4. So apparently Bill is a better or has a larger chance to hit the target, right? Bill hits the target with 0.7 probability, and George hits the target with probability only 0.4, right? Given that exactly one shot hit the target, okay? Now we are told that exactly one shot hit the target, right? What is the probability that it was George's shot, right? So what would you guess? So we know that Bill is better than George, and there is only one hit, then you would say that probably Bill, or you will say that Bill is more likely to hit the target than George, right? Am I right? So there is only one hit. One is a lot better in hitting the target than the other. Of course, you would just incline towards saying that, okay, whoever is better, he must have hit, right? So you would expect for George was can hit the target with less probability, the probability that the George must have hit, given that the target was hit only once, should be less than 1/2. But we need a precise number, right? So that's what the question is asking for, right? And the second part, it is a little bit more elaborate. It says, given that the target is hit, we don't know whether it is once or twice. We are just, well, we saw that there was a sparkle at the target, right? Maybe once or twice. Now what is the probability that the George must have also hit, or must have hit? I shouldn't say also, right? So these are two parts of the same question, right? Okay, let's take short notes, right? Two people, Bill and George, go together for target shooting, right? Right? Go together for target shooting, right? Independent of each other. Probability that Bill hits the target with probability 0.7, right? And the probability that George hits the target with probability, right? With 0.4. The probability that the George hits the target equals 0.4, right? Okay. In part A, right? Okay. We are told that, right? Target is has been hit exactly once, right? Given that exactly one shot hit the target, right? What is the probability? Okay, George. Okay, hit it, right? And in part B, right? So here the emphasis is on exactly, right? Exactly one. And here in the second part we have the question says, given that the target is hit, we are not told how many times it was hit, right? In this case we don't know that. We have less information. What is the probability that, again, George hit it? Right? So in one case you have more information, in the other case you have less information. But we would like to again insert the same, we would like to again find the same probability that the George was successful, right? Okay, right? So we'll again start by doing what? So lots of numbers and statements. It is all in English. We have to just translate this into problem where we can use again the probability axioms and perhaps conditional probability concept, right? So obvious ones, right? Obvious events. Let us denote by B the event that Bill hits the target. And similarly use G, right? To denote the event that George hits the target. Alright? What else? Okay. Well, we need to somehow express, right, denote the events that the target has been hit exactly once or twice, right? So you're free to pick any letter or any notation, but I just decided to pick H1. H sub 1, let us denote by this the event that the target was hit, right, exactly once, right? And similarly we can use H2 to denote the event that target was hit. Well, I don't have to say exactly, I guess in this case, well, we just, let's say twice, right? Since there are only two people, right? We don't need any other information. Similarly, you can also introduce H0, right? But H0 is what? Just the complement of the union of these two, so you don't have to do that. We can always use the complement of the union of these two events if we ever need to use event H0, right? If I just introduce this, first of all, we should never lose, right, the side of what we really want to calculate. What is it that I would like to calculate in this case? Well, for part A, how would you express that? Okay, let me just ask you. Huh? Now, whoever name I now remember, well, in danger, right? I will not do that. Who wants to just share his or her ideas? For part A, how would you express this question by using these two? Go ahead.
We want two independent events at the same time, which is George will hit the target and we want to hit the target.
Okay, so I will just start like, you should tell me like it is like the probability of such and such events.
George hits George.
So I can use this? Is it okay? Just let me use G, huh? Given that? B complement. So in part A, huh? So let me write it. Let's wait for A. Okay, let me see. Probability that George hits, okay, that's the second, this part. Okay, exactly, given that exactly one shot hit the target. I see you are saying far to the end. Yeah, I guess. Huh. Okay, intersection. You would like to calculate this, the probability that event G and complement of B happen at the same time. But you are reading it, I guess, correctly. I would just say the first one is a better way to describe this. So the given that means you already know that exactly one shot hit the target, right? And I cannot read that here, actually. Huh? So are you satisfied with this one first? Huh? No? Perhaps I would just wait for this one. I guess this is more closer to the answer. But even then, you are, I guess, mentally doing some of the calculations in your mind, and you just reach to the final stage. I would just try to find a way to basically use all these things to write immediately what is. Why would you mean here? Like this? Huh?
No, it's over, because we are conditional probability.
So all of them?
Over probability of H1.
You mean like this? Huh? You would divide this? No, you are making now too complicated. Any other suggestions? Okay, how about this? Read it in English. Probability. Probability that G stands for what? Probability that George hits the target given. It's exactly this one, right? I was just trying to make life easier. You are thinking more complicated than it is really necessary. I guess we can start with this, but I would just, okay, we'll see. I guess there is something to do with, there is a relation with these two things. If you especially open up, we will soon use the definition of conditional probability, right? Just to solve this one. But before doing that, okay, does everyone agree that this matches with this one? Anybody else? Any questions? Okay, that's, I guess, what we need to find for part A. How about part B? Before we solve the problem, let's just write it while we are at it. Okay, how would you write part B in terms of these 4 events? I again transpose it, but that's not important, right? What is, you know that you need to calculate the probability, right? It's a conditional probability because it starts given that. So you know something, right? You will want to use that information to make an inference about the likelihood of an event. That event is G. You would like to make an inference about the likelihood of this event, namely George was successful, right? You want to know the probability of that, but you are given further information, right? What is it? It is just hidden here, right after given that, right? Target is, oh, okay, hit. That's it. Target was hit, right? So we need to write something here and then close the parentheses. What is that information? Or I should say, how can you express that information in terms of this 4 events? Hit means what? It is hit. You don't know more than that. It is just to complement at the complement of the event that it wasn't, the target was not hit. Huh? If H0 was there, I would have just written like this. Oh, complement of that, right? If we had defined H0 as target was not hit at all, right? Because we know that it says, okay, target was hit, right? That's all we know. But what is H0? It is the complement of this thing. There are 2 people shooting at the target, right? Either one of them or both of them will hit. In any case, target would have been hit, right? Then actually, instead of introducing this lousy event, right? Well, there is already 2 of them. I could have just written like this, right? Either once, exactly once, or twice, right? No matter what the number of times it was hit, target was just hit. That's just summarized by this union, right? Do you agree with me? Huh? We are fine with it? Okay, that's what we want in part B. Right. Once you know what you need to find, right? Okay, then you have to just look at the question closer and identify what you have already learned, right? We will then use them to, together with all our knowledge about what all about conditional expectations are, to calculate the problem or to solve the problem, right? Okay, what do I know? Well, I know, right? I already wrote here, right? That probability of B equals 0.7, right? And similarly, I know that the probability of event G equals 0.4, right? And there is something else hidden over there, right? That the probabilities that Bill or George hit the target are independent, or event. I shouldn't say that. That's the wrong way of saying that. Events that Bill hits the target and George hits the target are independent of each other, right? Namely, events, right? B and G are independent. That's not like a number, but it is at least as strong as knowing just one of the probabilities, right? So you immediately remind to yourself what this means. Well, I shouldn't do that. I shouldn't do that because that's probably not what I need, right? Okay, so we'll soon see how we can use that independence information. But all what I am trying to say is the information about independence of the events B and G are at least as important as these numbers themselves. So if independence is given to you, you should not ignore that. If independence is not given to you, well, you shouldn't assume that events are independent and try to use it. That's also dangerous. Okay? So now, let's look at the first probability, namely this, right? In part A, now we all agreed that what we really want to calculate, or what we are asked to calculate, is this conditional probability, right? Then, well, you immediately, right away, use the definition of conditional probability. What is this? It is a quotient, right? 2 numbers, one divided by the other. In the numerator, you have what? The joint probability of events G and H1. And the denominator, you will have the probability of the event that you are told has happened. Namely, target was hit exactly once. Right? Now, forget about the probability. Now we have to understand first what this event corresponds to. Right? What is this? G happens at the same time as H1. What does this say? George, right? George hit the target, and the target was hit exactly once. They must happen at the same time. How can this happen? What must Bill have done in the meantime? Exactly. Right? Because if Bill hit the target, then the number of times the target was hit would be 2, right? That cannot happen. So this is equivalent to writing what? G hits the target, but Bill cannot, right? Why did I do that? Because I know the probabilities for these two guys, right? Okay, that's great. So the probability, if the events are the same, of course the probabilities are going to be the same. So I can write here the probability that G happens at the same time as complement of B, right? That's great. Now, what happens here? Well, what does this tell me? So target must have been hit, right, exactly once. What can you say about what happened to Bill and George? Right, exactly. Either Bill, should we start Bill? Right? So B says, okay, Bill hit the target, but then, what should I write? We must make sure that George did not hit. But this is only one side of the same story, right? And maybe then George might have hit the target, but then we should not, this is not nice. I should just read in the same order. I guess it is easier to read. So maybe Bill missed, right? But then for this to happen, George must have hit the target, right? So these are alternatives to each other, right? So we'll take the union, right? One of these two must have happened, right? Right? Yeah?
So, do they try only one shot?
Yes. They shot at the same time only once. Right? Okay. Maybe they shot to each other, I don't know. We could have actually formulated the problem like that as well. So, okay. Right? So we are fine with this, right? So what am I trying to do? Usually students just rush and try to write the probabilities. Before that, it is always good actually to take a look at the events themselves before you worry about the probabilities, right? So one event, if you can express it in any easier way in terms of other events, then the probabilities later can be calculated a lot easier, right? So I first just analyze the events and then write the probabilities. Okay, we wrote it here. Okay, do we know whether they are disjoint or not? Are they disjoint? Well, so I have two events that I take the union with each other, right? Are they disjoint? Can these two events happen at the same time? Huh? Who said yes? Okay. Let's take the intersection, right? So we are not quite sure whether this is true or not. So this is one. You take the other one, and you take the intersection, right? I wonder whether they have any common element or not. What is the result? Right? You take first, right, the intersection of B with its complement that all of a sudden kills all of the guys, right? So you have empty set from there coming, and then you have the intersection with another empty set. I mean, you don't even need to know what happens here, right? If empty set intersects with any other set, you of course get empty. So these are disjoint. So these two things cannot happen, right? Right? Two ways to check that is one, just look at the plain algebra, or just think again what happened. So here, either Bill hits exactly once, or here George hits exactly once. Well, these two things cannot happen at the same time. So they are disjoint. So the probability of this event, of course, is the same as the probability of the union of these two disjoint events. but the union of two disjoint events can be written as the sum of the probabilities of those events separately, right? Then, well, it is fair, right, to write like this. Complement goes here, right? Okay. It is not surprising to have the same numbers showing up here. Okay, now what do you think we should do? Do we know any conditional probabilities? Perhaps. Or do I need to do that? I don't know. What do you propose? Huh? Right. So we will use independence, right? It is always good to write, actually. I don't do that on my part, but well, you remind me just to. So we will use the independence, right? By the independence of events. B and G, right? We can write the probability, joint product of events B and B complement as what? The product of probabilities of the corresponding events. And in the denominator, what do I have? Well, this is the same as the numerator, so I can just copy that. And what happens here? Well, it can also be written as the product of these probabilities. Right? Are you satisfied with this? Huh? Somebody should at least challenge me. Must have challenged me, right? Okay, we know that B and G are independent, but how do I know that this implies, right? I'm not sure, that events B complement and G are also independent. Huh? Because B and G are independent means what? That's just a simple statement saying that, okay, if you ever need to calculate the probability that G happens at the same time as B, that can be found by just multiplying marginal probabilities. Right? That's what, by definition, independence of events G and B means. Right? But here I am using something different. Right? I said, okay, G and B are independent, by which I mean really this equality, but then I wrote something else. I said, okay, B, G intersection, B complement, probability of this joint event, right? This joint event, it sounds like the disjoint, but it is not, right? Can be written like this, right? And you should just stop and just raise your eyebrows, right? What's going on here, right? Can I do that? Is it legitimate? Huh? I'm trying to confuse you. It is true. If there is a result which says that, right? Result, so this is too much. Okay. If two events, let's say B and G, are independent, then B complement and G must be independent, and even B and G complement must be independent, and in fact B complement and G complement are independent, and the reverse are of course bisymmetric correct, right? That's a result. So I use this independence of event B and G and wrote this not because I am careless, but consciously I use that because I know that independence is contagious. If two events are independent, their complements in any order are going to be independent, right? Okay, then we can come back to this and then, right, calculate this thing. All we have to do is just plug the numbers in, right? Probability of G is 0.4. Then what do? Probability of B complement is what? Probability of B is 0.7. So 1 minus 0.7 is 0.3. Have I made a mistake with this? No, right? So 0.4 times 0.3, I can just copy that, right, for this point. And plus No, B complement. Its probability is the probability 1 minus probability of B, which is 0.3. Huh. Have I made a mistake? Which one? I messed up with this?
First one is
G.
G complement multiplied by B.
I was just following this. Yes. So the probability of G is 0.4. Huh? Am I right? I'm not good at this.
But there G complement multiplied by B.
G complement. You are talking about this, right? You are right. What have I done here? Is this correct? This is correct. I see. This should have been B, right? And this should have been G. Knowing only the independence is not enough to solve a problem, right? Okay. What is, okay, so let's look at the B times probability of G complement. Of course, then I cannot do this. Is it the second part though? Yeah, these are the same, right? Okay, let's just follow the same order. So for B, it is 0.7. For G complement, the probability is 0.4. Sorry about that. And this is probability, so this is supposed to be the same, even though the order is different, right? Okay, just to be strictly correct, okay, let me do it like this. Okay, let's just quickly simplify this. This is 28 plus 12, right? So 12, what is this? What? Have I... Okay. Have I made another mistake? I am just rushing to the end and then I'm making mistakes. Now when you say just the numbers, I cannot follow at all. So this is correct, right? This is correct. And we are fine. Is it fine? For B, I see. Right? 0.6. Oh, okay. How about this? This is correct. And this is 42 then, huh? I mean, okay. And then this is 54, huh? Now I'm really slowing just to make sure that I don't make... Huh? 2/9. Thank you. Okay. This is, as we expected, is a lot less than 1/2. Right? That's what we expected. Okay. Okay, for part B, okay, let's just give it a break and then we can come back and quickly. Am I going slow? Huh? How do you feel about it? Huh? Is it okay?